Yeah, so hope my screen is visible now, right? Okay, so far we discuss we learn about the first law of thermodynamics and some applications on this. So we also discuss the various thermodynamic process. Okay, so mainly so the thermodynamic process. So various thermodynamic process included the isothermal process, isothermal process, and second is the adiabatic process. And other process isobaric is also discussed. So so these two process are and we also tell that we also learn this thing that these two process are the reversible process, right? So this process must be the reversible process. So what is mean that the reversible? I'll come to this point after a few minutes. So so the most general process, so the most general process is that the polytropic process. Okay. So so today we will discuss briefly about the polytropic process and do some problems on that. So the polytropic process is the most general process. So it's the polytropic process. So what is the polytropic process? Is that p to the power n equals to constant. Okay, and where n is the polytropic index. Okay. So where n is the polytropic index and p to the power n equals to constants. So you first know that the two things that just a minute. Okay. So you first note that the process and the equations of states two are different things. Okay. So equation of states tell that the f p v t some function equals to 0. Some functions of pressure, volume and temperature equals to 0. So this is the equation of states and the process, and pv to the power n or pv equals to constants for isothermal process, adiabatic process. Similarly, you know, right, pv to the power gamma equals to constant. So the process or equations of state are two different things. So once you calculate for let's say, once you provided that the which equations of states are using, and we calculate for a particular process for these equations of states. Okay. So we calculate, let's say, for any kind of ideal gas or any kind of real gas. Okay. And the process, you calculate some particular process for ideal gas or any kind of real gas. Okay. So these two things are different. So the process and the equations of states. So the polytropic process that p v to the power n equals to constant, and so we'll then we the first derivatives on this. So what we get that n p v to the power n minus 1 dv plus v to the power n dp equals to 0, right? So then v to the power n minus 1 factor out, and then we get that np dv plus v dp equals to 0, right? Okay, and let's consider the ideal gas. For simplicity, we consider the ideal gas. So the equations of ideal gas, the pv is let's say nu RT. So nu is the number of moles. Okay, or okay, so let's first consider pv equals to RT. We consider 1 mole ideal gas. So ideal gas 1 mole. Okay, and the equations of state is pv equals to RT. So now we calculate. So in this case, then what we get that P dV plus V dP equals to R dt, where R is a constant, is a gas constant. So then in the previous class we derived that dq. So this d cut means that this is a inexact differentials. So dq is cv dt plus, what is the relations that in the previous class we derived that the general dq is yes, so this relation, yes, this relations. Okay, so dq is del u del dp, this is your cv, so cv dt plus del u del vt plus p dp, right? Yeah, so if you calculate for this polytropic process, cv dt plus plus r by 1 minus n dt. We just replace this p dv and v dp with in terms of r dt. So if we replace this, once we get this dq actually cv dt plus r by 1 minus n dt, right? Then then what about the dq by dt? This is nothing but the cv dt plus r by 1 minus n. What is this quantity? This is the specific heat. So not the particular volume or not a constant volume or constant temperature. This is in general the specific heat C. This is at constant volume cv dt plus r by 1 minus n. So we denoted that this C n because this is the for polytropic process. Okay. So for a particular process and polytropic index n, we denoted that this is a Cn. Okay. So that does not mean that this n here is a constant n. Okay. So n actually denoted for that for a polytropic process or polytropic index n and the corresponding specific heat no, the heat capacity is a Cn, and this Cn, this Cv dt plus r by 1 minus n. Yes. Okay. So then, so now we put that what is your R for ideal gas? For ideal gas, you know that the Cp minus Cv is actually R, gives a R. Okay. So then you put that Cv dt plus Cp minus Cv by 1 minus n. Just a minute. I think there is a dt. Oh, there is a no dt, right? Yeah. So then we just simple little bit algebraic, so that the Cv is Cv times n minus gamma by n minus 1. Right. So this is a Cn, where gamma is actually Cp by Cv. So that means, so this is a, in general for polytropic process, the heat capacity, the formula for the heat capacity by Cn is Cv times n minus gamma for, by n minus 1, where gamma is actually Cp by Cv. So this is for in general. Now we are calculating for different limits, where go to the isobaric process, isothermal process. So let's first draw that the diagram, PV diagram for different values of n. Okay. So this is P and versus V. So let's say for n equals to 0. For n equals to 0, so P v to the power n equals to constant. Okay, and we are putting into the different limits. So n equals to 0, and then this process is called so that this implies that the p equals to constant, right? So this is a isobaric process. What about n equals to 1? For n equals to 1 means that pv equals to constant. So this process is called the isothermal, right? What about n equals to gamma? So n equals to gamma implies that the p v to the power gamma equals to constant. It's called the adiabatic. What about n equals to infinity? N tends to infinity. Can you tell me that what about what is the n goes to infinity implies? So this is a polytropic process. Pv to the power n equals to constant. So n tends to infinity is implies that can you tell me that what this limits goes into the process? Means that n equals to 0 implies that p equals to constant isobaric process. N equals to 1 implies that pv equals to constant isothermal process, and n equals to gamma. So pv to the power gamma equals to constant. This is a adiabatic process. So n equals to implies n equals to infinity, n tends to infinity implies which process? Yeah, good. So this implies that isochronic process. How to know that? This is just a p to the power 1 minus n v equals to constant. Okay, then we put n equals to infinity, so 1 over infinity goes to 0, so v equals to constant, right? So this is an isochronic process. So this is a general for any n calculate for I am considering this for different values 0, 1, gamma, infinity. So in general this pv to the power n equals to constants. I will do some problems that where this n actually comes 2, 3, 4, okay, different values. So in general this, so if you plotted this so that the bound is that, so isochoric this for n equals to 0, right? Pressure constant, sorry, isobaric n equals to 0, isochoric so this is isochoric, okay. So this process, so this put this is keeps that n equals to, sorry, n tends to infinity, right? And other two process is that n equals to 1 and n equals to gamma. So pv equals to constant, so this process, and n equals to gamma, this process. So this is n equals to 1, n equals to gamma. So if you put any value n equals to 2, 3, 4, okay, so different process are given. So all are in between n equals to 0 and n equals to infinity, right? So in between there are. So if you know that why this n equals to gamma is more steeper, just to takes on more derivatives, del p del v. and we say that this is just steeper than the isothermal process, right? So adiabatic process is steeper than the isothermal process because gamma is always greater than equals to 1. So this implies that this adiabatic process more steeper adiabatic process more steeper than just a percent. No, yeah, adiabatic process more steeper than isothermal process. So then if this is n equals to gamma, n equals to 1, define process. So now we draw this heat capacity for this process, okay, and what it looks like. So this is just in general heat capacity. This Cn equals to Cp times n minus gamma by n minus 1. Okay, this is a general formula for polytropic process of the heat. General formula of the heat capacity for the polytropic process. Right? So a similar types of we draw this plot diagram with Cn versus n. So this is a Cn, okay, and this is a n. So let's say we denote this point H Cp and this is Cp. So considering ideal gas, so Cp minus Cv equals to R, right? So that means Cp is Cv plus R. So if you consider this Cv, then Cp is R. So Cp minus Cv is always greater than 0. So if you do any real gas, okay, then we calculate the Cp minus Cv. So I will derive later that is the general formula for the Cp minus Cv for any kind of gas, okay. And we see that the Cp minus Cv is always greater than 0. So Cp is always greater than Cv, okay, for isothermal process, or sorry, not isothermal, for process in thermal equilibrium, okay. So the Cp is Cp is always greater than equals to Cv, and so then with that's Cp and Cv, and so let's say this is n equals to 1, this is n equals to gamma. So we draw a cut line, n equals to 1, this is gamma, and goes to. So let's change my color. Yeah. So now put n equals to 1 in Cn formula. So what is the formula for Cn? Is Cv times n minus gamma by n minus 1. Yeah. So we are considering ideal gas. Okay. So this formula. So that one is the gas equation and another is the process. Okay. So we consider ideal gas and polytropic process. So we end up with this formula Cn equals to Cv times n minus gamma by n minus 1. Now put n equals to 1. So n equals to 1, that means Cn goes to diverge, right? But n less than equals to 1, let's say n equals to 0. So first put n equals to, let's say, 0. How do we get that? Cn Cv times gamma. So what is gamma? So Cv times gamma, right? So for n equals to 0, yes. So this is nothing but the Cv and Cp by Cv, right? Gamma is Cp by Cv, the ratio of this Cp by Cv gives the adiabatic index gamma, right? So then this is Cp. So at n equals to 0, we start this point Cp, and at n equals to 1, at n equals to 1, Cn goes to infinity, diverge, right? So that means they will increase in this way, right? So at n equals to 1, so this is n equals to 1 line, so this is increase in this way. So now put n equals to gamma, then Cn is Cv times third. It's 0, right? So it's 0. So n equals to gamma, okay, Cn is 0. Okay, then let's put n goes to infinity. Cn, can tell me n goes to infinity, Cn goes to, hello. Okay, so in n goes to infinity, just put there, right? So Cb times, how to calculate this, 1 by gamma minus n. Let's say divide by n, so 1 by 1 minus n. Now n goes to infinity, this quantity goes to 0, this term goes to 0, this term goes to 0, so you end up with a Cb, right? So that means at n goes n equals to gamma, Cn 0, at n goes to infinity, Cn goes to Cv. So this process is like this. So they hit Cv at n goes to infinity, right? So at n goes to infinity, they hit Cv. But what about in between, n equals to 1 and n equals to gamma? So if you calculate that in between, that n is, suppose n is less than gamma, n is less than gamma, right? So gamma is always greater than equals to 1, right? So gamma is greater than equals to 1 and n less than equals to gamma. That means that n minus gamma is less than equals to 0, right? And n minus 1 is greater than equals to 0, because, yeah, so n minus 1 is greater than equals to 0, right? We are considering that in between any points, let's say this point, okay, so this point, so in between this point, so that means that Cn is negative, negative. Actually the process is that in between we get this process. If we plot for various values of n, and we get this kind of curve. So again at n goes to infinity, they goes to minus infinity. But in this case, for if we go n goes to 1 from the left side, we get the upper, we go into the divergence, the positive infinity, and when we go from the right sides, when we come from the right sides, okay, so then it goes to the negative infinities, okay, so again goes to divergence, right? So that means the any process, so this is the heat capacity looks like for a polytropic process for various values of n, okay, so there is a divergence at n equals to 1, okay. So one important point here, that Cn is for any values of n, they are it's not happier here, right? So in this region. Okay. Okay. So this point is clear or not? Okay. So next we calculate yeah. So what things we have to calculate? Yeah. So let's say for now we calculate, let's say delta Q, the change in heat delta Q. So what is the formula for delta Q? Delta Q is the formula that written here. This for polytropic process. So for a finite change delta Q, so they just think the infinite will change, right? So that's why that's why we are denoted this small d. But for a finite change delta Q, we are calculating this Cv delta T plus R by n minus 1 delta T. So now you know that the Cv is R by gamma minus 1 for ideal gas, right? For ideal gas. So this actually just how to derive. So this is very easy to know. So you can know that how to, yeah. So the Cv actually dq dt at constant volume. Okay. So for ideal gas, you write the equations, okay, and you get this Cv R by gamma minus 1. We also derived in the previous class. So then we put this formula R by gamma minus 1 plus R by n minus 1 times delta T. So this is n minus gamma times R by n minus 1 times gamma minus 1 times delta T. Right? So this is a change in the heat. Okay. For polytropic process. So if you calculate for ideal gas delta U for ideal gas delta U is CVDT delta T, right? Okay. So for in this case delta U is Cv is R by gamma minus 1 times delta T. So this case is not depend on the polytropic index n, right? But delta Q is depends on the process. Okay. The depends on the explicitly on this polytropic index n, right? So let's do some problems so that it becomes more clear. So one example is that let's say we consider a process where Vt equals to constant. Let's say consider a process where Vt equals to constant. Right. So consider a process where Vt equals to constant. And we are giving the ideal gas. So that means that Pv equals to RT 1 mole ideal gas, this PV equals to RT. So this process is nothing but that PV square equals to constant, right? So once you specify that the equations of states, that means how the P are related with the V and T. So you just replace this T in terms of pressure and volume, we get that PV square equals to constants. So this is a polytropic process with polytropic index n equals to 2. Right? So n equals to 2. So it's a polytropic process. So this is a polytropic process with polytropic index n equals to 2. Right? So then, so if we if we ask that what is the change in the heat delta Q in this process, okay, so once you know that n equals to 2, we just put into the formula and we get the values, right? So then I just put into the formula, what we get that delta Q R times n minus gamma 2 minus gamma by 2 minus 1 into gamma minus 1 times delta T. Right. So this is a change in the heat due to the change in the temperature delta T. The change in the amount of heat delta Q is R by 2 minus gamma by 2 minus. Right. Similarly, suppose do another example, so a more complicated process. Let's say U. Okay, so let's say P equals to alpha B. This process. So this implies that PV inverse equals to constant. Right. Yeah. So n can be positive, negative, any values. So there is no restrictions on m. Okay. So here I am only plotting for the positive values of m. Okay. So but n can be negative, so as well. So in this process, that n equals to minus 1. So then if you calculate the delta Q for this process, just put into the formula and you get this gamma plus 1 by gamma minus 1. Okay. Into delta T. Right. So due to this amount of temperature changes delta T, the amount of heat changes is delta Q is this. Okay. For this process. So next, if we do the another process, let's say U is A V to the power alpha. So let's say for the process is given that U in terms of V. Right. So first task, we have to convert this in terms of polytropic process. Okay. So how to convert? And we are provided that all are the process in ideal gas. Right. So what is the U for ideal gas? This is a delta U for ideal gas, CV delta T, right? So that means U is CV T. So put into that CVT equals to A V to the power alpha. So this implies that T V to the power minus alpha equals to constant, right? This is right. Or if you know that the U is proportional to temperature, right? Some constant. So U is actually, what is that? 3 by 2 RT, right? For monatomic gas. For monatomic gas, right? So you know this. So that means that T v to the power alpha, so U is proportional to temperature only for ideal gas. For ideal gas. For ideal gas. Okay. Yeah. So for ideal gas, that you know that the U is proportional to temperature, so we end up with this process. So now convert to the using the equations of states, we convert into the polytropic process. So we do that P v to the power 1 minus alpha equals to constant. Okay. So that is, this is a polytropic process. Polytropic process with polytropic index n equals to 1 minus alpha. So this polytropic process important for your entrance exam anywhere. So, okay, so this process we had to various types of this kind of given this and we just converted this into the polytropic process, and then we know, once you know the n, we calculate the delta q any other quantity. So then we replace this what about the delta q for this process, so we just put into the formula. Okay, so you get that yeah, I think what about the delta q r by minus 1. Yeah, so you say that the r by r minus 1 and n minus gamma by n minus 1. So it's that r by r minus 1 1 plus gamma minus 1. Right. So this is the expressions of the delta q. So what is the work done delta W for polytropic process? How to calculate? Simple, that P dV, right? And this is V1 to, let's say, V2. This Poriman changes. And if you want to put that P V to the power n equals to constant, so dV by V to the power n, some constant C. P V to the power n equals to some constants. Okay. So then this V1 to V2. Okay. So this is simple, that minus C V2 to the power minus n plus 1 by 1 minus n, right? So now this C P to the power minus n plus 1 we replace in terms of, sorry, on minutes there. So this constant, put the constant, so minus, that means P P2 P2. So P, so at any point P2 to the power n equals to same constants, right? P1 to the power n equals to same constants. Okay, so that means we put that C value P2 V2 to the power n. So that means this P2 V2 minus P1 V1 by 1 minus n, right? So that means P1 V1 minus P2 V2 by 1 minus n. Now if you consider ideal gas, so this is nothing but the RT1 minus RT2 by 1 minus n. right? So that means this delta W H R by 1 minus N times delta T. Yes, so delta T is T2 minus T, or there is a minus. So this minus sign is just a convention. Okay. So up to this point, any questions? So, so if you consider the so far we consider the polytropic process and calculate the delta Q, delta W. Okay, for in general values of n. Okay, so if you put on any one of values of n, we get the specific process. Okay. Yeah. So up to any point, any questions? Okay. Okay, so let's do one more process. Okay, so this is not a polytropic process. Okay, this process is different. So let's say the process is that T equals to T naught into e to the power alpha b. This kind of process, right? So this process is not anymore the polytropic process. Okay, you cannot convert it to the polytropic process. So then let's say calculate the heat capacity for this process. Okay, okay. So we calculate the heat capacity. This is the Cn for polytropic process, and then we calculate delta Q, the change in heat due to this change in temperatures for polytropic process, and delta W, we also calculate delta W, and we also calculate delta U. Why we calculate delta U? Yes, this is the delta U, and delta U is does not depend on this polytropic index, right? Because the first law of thermodynamics tells that the delta U equals to delta Q plus delta W, right? So for irreversible change, and if you calculate this thing, that delta U is independent of the n, but delta U, delta W is dependent on this n. Okay. So now we are considering the process. This is not a polytropic process, but we calculate the heat capacity for this process. Okay. How to calculate? So the first things we calculate the change in temperatures dt, the derivative first, and then the T naught times alpha times e to the power alpha b dv system. Okay, so then this dv is 1 by alpha T naught to the power alpha b, sorry, minus alpha b, right? So why we calculate this? Because if we define that C, the heat capacity, C, this is dq dt. I'm putting card here because this is not in exact differential. So and we know that the in general formula for this dq dt. Okay, so in general formula is dq dt is that cv plus, what is the general formula for this just only pdv? Yes, yes, yes. So then this dq dt, right? So that means cv plus dp dt, right? So this is a dq equals to cv dt plus p dv, right? Are we calculating dq by dt? So this is cv plus p dv dt, right? So then we once you know this dv dt, we just put into there, right? So cv plus, what is p for ideal gas? Ideal gas. Again we consider the ideal gas. So p is RT by v. So RT by v times dv dt is 1 over alpha t naught e to the power minus alpha v, right? So that means we get that cv plus, yeah, cv plus, yeah. So now we put into here into there, right? So this is your t. So you put t naught in terms of t. So just check. Just put it t. Okay, so t naught e to the power alpha v, v alpha t naught e to the power minus alpha v. So e to the power alpha v e to the power minus alpha v cancel, t naught cancel. So c is cv plus r by v alpha, right? So this is a process. So this is a process. Okay, and this is equations of state, right? And we get this for this process. Similarly, the other process is not a polytropic process, this kind of process. So we calculate first dvdt and just put into the formula. Okay, the heat capacity, you get the heat capacity for this process. Yeah, so up to any point, any question? Okay. Okay, so now going to the concept is the reversibility. Okay, what is that? So previously I told that this process must be reversible. Okay, so the isothermal process and the adiabatic process, this must be the reversible process. Okay, so what does this mean, that reversible? And then we go into the Carnot engines. Okay, why we need engines, and discuss the second law of thermodynamics and a little bit about entropy. Okay, and then we'll go into the assignment problems. So I think till then the most of the problems is solved during this. In the meantime, so the reversible. Okay. So what does the reversible process means? Okay. So first of all is the adiabatic process. Let's consider the adiabatic process. So adiabatic process is two kinds. One is that adiathermal plus reversible. Okay. So the reversible process is means that, so this means that adiathermal means that the no change of heat, and reversible process means that we use this dw equals to minus pdv. So this is a equal sign. So this means that the reversibility. Okay. And if we use this dq equals to 0, the no change of heat, and dw equals to minus pdv, then we end up with this pv to the power gamma equals to constants. If any of these conditions is fails, then we cannot tell that the PV to the power gamma equals to constants. Okay. So this reversible is important. Okay. So reversible means that any process. Okay. So if any process is allowed, if any process is allowed, then the time reverse process also allowed. Then the time reverse process can also occur. So this is the basic the, means that the reversibility. Okay. So which process is not reversible? Yeah, but very specific. That let's consider a battery. Okay, and this battery and drives a current through this wire I, right? And due to this current, the wire dissipates the heat is I square R. Right? So heat dissipates. This is a battery. Okay. And the currents are and the voltage is V. So if the resistance of this wire is R, the heat is dissipated at the I square R. So this process is an irreversible process. Right? We cannot get that back to the same amount of heat. So once it dissipates, it dissipates into the environments. Okay. Never find it being absorbed by a resistor from its environment. So heat already dissipates. Heat dissipates into the environment. So they never find heat being absorbed by resistance from its environment. Okay. So one never finds heat being absorbed by resistors from its environment. Okay. So this is a typical example of an irreversible process. Okay. So then yeah. So suppose that the problem is that we are considering the isothermal expansions, okay, and the compressions of the gas. Okay. So why we need the reversal? So let's say the isothermal compressions or the compressions of the expansions on the gas. Compression and expansion of gases reversibly. What this means? It means that how to do the reversible process? If we do it sufficiently slowly, so if we do it gases compression and the expansions of the gases reversibly, if we do it sufficiently slowly, so that the gas, remains in equilibrium throughout the entire process. Throughout the entire process. So this statement is very important. So remains in equilibrium throughout the entire process. Okay. So that means, so let's say this is a, so we are saying that the temperature is isothermal process. Isothermal process. And we consider that the PV, right? So at any point, let's say this point, sorry, let's say this point, let's say this point. Okay. So in this point, the P1, the pressure is P1, volume is V1. Okay. The pressure is P1, volume is V1, right? So this is one equation of states at a particular temperature T1. For the second process, you say that the P2, V2, right? But the temperature is constant. So when these two systems is the same temperature in thermal equilibrium, right? So the two systems, one and the second system, two systems, if we connected these two systems, let's say this is a temperature T1, this is a temperature T2. But in thermal equilibrium, the two systems is a common temperature T, right? So that means these changes, okay, so this one state to another state is so slowly such that they are in equilibrium is always, right? So temperature does not change means that the two systems, system 1 and system 2, are in thermal equilibrium, right? So if we suddenly change from, let's say, this point to, let's say, this point, we suddenly change from this point to this point, right? So that means they are not equilibrium, right? They are not equilibrium. So you lost the things that, and this is a irreversible process. Since that if we suddenly compress the gas, okay, and they generate some shock waves, okay, and due to these shock waves, the heat produced, okay, and so this is a irreversible kind of process, okay. So if we change slowly, so that the gas remains in equilibrium throughout the entire process. So we change the inference field slowly from this point to this point, such that they are in the same temperatures. And again, we have from this system to these systems, again they are same temperature. Okay. And in this way, we are slowly going to this process. Okay. So that is called the reversible process. And one, you know that in the reversible process, you say that the temperature is constant. So once you go this P1 V1 to P3 V3, suddenly you cannot tell that this is a reverse for an irreversible process. Temperature might not be constant. So if you have to constant that the temperature is constant, then you can slowly change from P1 V1 to P2 V2 for an infinitesimal change, right? So this process is called the quasi-static. Okay. So this process is called the quasi-static. So each equilibrium state, so this is a one equilibrium state P1 P1 and another equilibrium state is P2 P2. So each equilibrium state differing from the previous one by an infinitesimally change in the system parameters. So quasi-static means that each equilibrium state state differing from the previous one, differing from the previous one by an infinitesimally change infinitesimal change in the system parameter. What are the system parameters? The system parameters is the pressure, volume, temperature, right? So the P1, V1 and temperature T1 and P2, V2, if you see the same temperature, that there must be the infinitesimal. Otherwise, you cannot tell that the two systems are in same temperatures, right? So the infinitesimal change is important, and if you want to do the infinitesimal change, that means they are the same temperature, and that means the isothermal process is irreversible. So this implies that the isothermal process is a reversible process. So isothermal expansion or compression must be reversible. It must be reversible. So we can go back and forth. Okay, so there is a no change. So once you know that every process, and let's say this is a expansion, that means we are going this direction, right? For compressions, we are going to these directions. Okay, so you compress the gas, the volume is decreases, right? So there must be the same. Okay. So once you use the formula for the expansions of the gas, and use the same formula for the compressions of the gas. Okay, just the sign is different. So, but the expression is the same. But for irreversible process, this might not be happens. Okay. And similarly for the adiabatic process, same case. Okay. So the adiabatic process, there is no change in heats, right? So that means for adiabatic process, the heat is nevertheless be absorbed or emitted in the process, maintaining the reversibility. So for adiabatic process, the heat can nevertheless be absorbed or emitted in the process. Okay, so heat is nevertheless absorbed or emitted in the process. Okay, while still maintaining the reversibility. Maintaining reversibility. Let's say you compress the gas. Okay, so by the pistons. So that means if there is a no friction, right, and you slowly down at the piston, and then there is a the process is reversible. But if you suddenly drop the pistons, okay, then what happens that they are produce some shock waves, and due to the shock waves they are generate some heats. Okay, so this is an irreversible process, and for the reversible process, heat can nevertheless absorbed or emitted. So nevertheless absorbed or emitted. So, and this is the indicate that the reversibility. So friction is the one of the dissipation. Okay, this is a irreversible process. Okay, so friction dissipation is the one of the example for the irreversible case. Okay. So then you may ask that for any kind of process, if you to do it by reversibly, it takes an infinite amount of time, right? If it changes slowly, then from P1 V1 to P2 V2, we have saying that the index might be infinite amount of time. So this again is a very long time, but we are taking a approximates of a real things, right? So we are taking a approximation since that it can be happened so in real situations approximately. Okay. So this the one more thing is that the reversibility requires the absence of frictions or dissipation. So reversibility requires the absence of friction or dissipation. So absence of friction or dissipation. This is the reversibility requires. If there is a friction or dissipation, the process is irreversible. Okay. So up to this point is clear. What is means to the reversible process? What is means to the quasi-static process? Okay. Yeah, so now come back to this point. Okay, so where we discuss yeah, so this is a ideal thermal process, no change of heats, dq is 0, and reversible process dw equals to minus P. So for irreversible process, what is happens that okay, just a minute. Yeah, so for a irreversible process, for an irreversible process, okay, because means that there is a frictions or dissipations, this kind of things are there. This dq, okay, not dq, dw is greater than equals to minus P. So it's not just the equal sign, but it's a greater than equals to minus P. So more work done in this process. Okay, we will come into this point later. Okay, so we will summarize other things. Okay, so let's first go into the engine. Okay, so why we need engines? So then we discuss about the second law of thermodynamics. Okay, so what is the second law of thermodynamics? Yeah. Okay, so in the previous class I am told that the two system again. So this concept is very important. And so let's say this is a T1 and T2. so put in a thermal contact, so they end up with the same temperature, right? So that is the thermal equilibrium. Okay, so when you connected the two systems at different temperatures and putting in the thermal contact, they end up with the same temperatures. But the heat flow from hotter body to colder body, how do I know, right? So the second law of thermodynamics can be formulated as a statement about the directions of the heat flow occurs as a system approaches equilibrium. So we know that when we connected the two systems 1 and 2, they end up with the same temperature, that is called a thermal equilibrium. Right. But the second law of thermodynamics, second law of thermodynamics can be formulated as a statement about the directions of the heat flow when the system reaches the equilibrium or approaches the equilibrium. So heat is always observed from hotter body to colder body, and the reverse process in isolations never occurs. What this means that the in isolations never occurs means that if we not put, suppose you put a power source, okay, so it's like a refrigerator, right? So in the refrigerator, heat is sucked out from a cold food and squirted out to the back into the warm kitchen, so that the heat flow from the wrong directions, from a hotter body to colder body to hotter body, right? So then in this case that if you in this case this work is done by the refrigerator motor. Okay, so the motor is work in this case, and they need some electrical power, this kind of things. So you put external source, but in isolations heat can never going from the colder body to hotter body. Okay, so the in isolations, so the no process is, that means that the no process is possible whose sole result is the transfer of heat from a colder body to hotter body. Transfer of heat from a colder body to hotter body in isolations. So this is important. And which sole result means that if you not put any let's say some part of this process, okay, and you say that the some part of the process is possible, but sole result collectively if you consider a complete process, then you cannot say that the no process is possible, that the heat transfer from a colder body to hotter body. So sole result. So this statement is called the Clausius statements. So there is two statements in the second law of thermodynamics, that the two statements are equivalent. So this is a Clausius statement. Clausius statement. Okay, so up to this point, any questions? Okay. So now, what about the other statements? Okay. So now the other statement is that so in this case, so the first statement is that the no process is possible from transfer the heat from a colder body to hotter body. But what about the energies, right? Changing energies. So how it is very easy to convert the work into heats? For examples, okay, so let's say okay, so energy are equivalent to a heat and work. Right? In the first law of thermodynamics, say that the energy is a sum of the amount of heat and plus amount of work. Right? So that means how it easy to change from energy, change of energy from different forms, means that it work or heat, how to change. So in particular that the work and heat, right? So it is very easy to convert work into heat. Okay, so let's do it systematically one by one. Okay, so the Kelvin statement tells that is that no process is possible, no process is possible whose sole result is the complete conversions of heat into work. Work. So this is the whose sole result. So there are two things important, that the whose sole result and the heat into work. Right. So how it's easy to change energy between the different forms, in particular work and heat. Right. So if it is conclusion is that the convert the easy to convert work into heat, but not the opposites. Okay, so in the saying that the no process is possible whose sole result is complete conversions of heat into work. So the complete conversions of the heat into work is not possible, but the complete conversions of the work into heat is possible. That's why the Kelvin statement uh, is a different statement from the Clausius statements. So but once you do that things, there are way to equivalence this thing, but the things are different. Okay, to different concepts. Okay, but one can show that they are two things are equivalence, but they are two different concepts. Okay, and they are not connected. Because in the Clausius statements, they tells about the directions of the heat flow, and the Kelvin statements that tells about the form of the energy, transfer from one form of energy to another. So which is possible, which is not possible on these regards, right? But the complete conversion of the complete conversions of work into heat is possible. I'll show mathematically. Okay, so how this is possible and this is not, right? So this is which is possible, which is impossible. So that's why the Kelvin statement state that. Okay. Okay, so this the difference between the two statements is clear. Okay, so now we say that the Kelvin statement of the second law of thermodynamics tells that the cannot completely convert heat into work, right? That means the some conversions of the heat into work. So that means that some conversions of heat into work is possible. Is possible. Is possible, right? So not the complete conversions, 100%, but few percent of this heat into work is possible, right? So that means that how good a conversions from heat into work is possible. Okay, how good is possible? How good is how good a conversions from heat into work. Okay, so how good? Let's write a complete statement. How good a complete good a conversion from heat to work is possible. So then we introduce a concept of engine. Introduce the concept of engine. To answer these questions, we are introduce a concept of engines. Okay. So we define an engine as a system operating in a cyclic process that converts heat into work. So why we need a cyclic process? Because engine operates repeat and repeats, okay, to produce a steady power. So it's not the engine that operates only once. So it operates repeat and repeat again and again, okay, to produce a steady power. That is the engine. Okay. So we need a cyclic process, and so that means we define an engine. So define an engine as a system operating. So engine as a system operating a cyclic process that converts heat into work. That converts heat into work. Okay. So cyclic means that cyclic. So there are too many things. That one is the engine. So it's a system and the operator is cyclic and that heat into work. So cyclic means that it operates again and again continuously. Okay, and producing a steady power. So it is such that the continuously operated. Such that continuously operated. Okay. Continuously operated. So such an engine for a reversible process. So this is a cyclic process. Okay. If we consider a reversible process, and that is called the Carnot engines. For reversible process, for a reversible cyclic process, for reversible cyclic process, we call this is a Carnot engine. So again, the Carnot engine very specific. Okay. a reversible cyclic process. So any real engine, there might be irreversible, but cyclic process it's okay, but there might be irreversibles. Okay, for real engines. Of this case, so these things are there, but the Carnot engine is very specific for a reversible cyclic process, and there are particular process are considering in the Carnot engines that so this process contains the Carnot engine yeah contains a cyclic process. This process contains that a reversible isotherm, right, reversible adiabatic, and then goes to again reversible adiabatic, reversible isotherms. So two adiabatic, two isotherms, reversible, right? So let's say this is A, this is B, this is C, this is D, and this is a PV, right? So AB and CD are reversible isotherm. Reversible isotherm, and BC and AD are the reversible adiabatic. Adiabatic. Right. Carnot engine is a cyclic process. A to B to C to D. This cyclic process is the Carnot engine. Okay, and they contain two reversible isotherms, two reversible adiabatic. So this process, this system is called the Carnot engine. Sorry. Any other process contains the reversible process. This is not a Carnot engine. Okay. Carnot engine is very specific for this. Okay. Okay. So up to any point, any questions? Okay. Yes. So that means that engine operates. So in A to B process, there are some temperatures, isothermal temperature, let's say TH, and C to D. So this is again isothermal process. There are different temperature, let's say TL. Okay. It's a high temperatures and this is a low temperatures. So then we define a reservoir. Okay. So what it means that the reservoir? So reservoir is the body which is sufficiently large that we can consider it to have a essentially infinite heat capacity. So this means that you can keep sucking heat out of it or dumping heat into it without this temperature change. So the infinite amount of heat capacity is there, so they can store, but you just you can if you keep sucking heat out of it or dumping heat into it without it changing the temperature. So reservoir, the concept of reservoir is that, so the reservoir is that you can keep sucking it out or out of it or dumping it into it without its temperature change. Without its temperature change. Right, that is called the reservoirs. So in this case, this TH, let's say, is a one reservoir and TL is the another reservoir. So schematically, we draw this Carnot engine in this way. Yeah, this one. So schematically we draw this, let's say answer reservoir. So this is one reservoir, let's say TH, and another reservoir is TL. This is a high temperature and this is a low temperature. And you consider an engine here. This is your E engine. So that means the heat in this from this reservoir and it put this reservoir Q out and some work done down. So Q in, that means the heat sucking in the heat out of it from this reservoir TH, Q in, sorry, yeah, this reservoir, and dumping into heat Q out in this the second reservoir TL. So this is a first reservoir and this is a second reservoir. So and the amount of work done is W. Right. Then we define a efficiency. Right. So okay, by the way, what is the work done W? So in this case, work done W is so this is your work done by the engine, work output by the engine. So this is your work output by the engine. Work output by the engine. And we say that this is cannot convert the this sole conversions of heat into work. Okay. So that means we define the efficiency of an engine, that how good it convert from the heat into work. Okay. So that is to define the efficiency. Yeah. So it down. So it defines in this way that what you want to achieve and what you have to do achieve it. Okay. So the efficiency defined in this way, that what you want to achieve and what you have to do achieve it. Have to do to achieve it. So this is a very general definition of the efficiency. And in this case, that what you want to do achieve, this W, and what you have to do to achieve it is Q in. Right. So this is the definitions of this. This is a work done W. This is Q in. Right. So this is a heat input and this is a total work done. So that the total work done and put a heat input, and we say that this heat input is complete conversions of the work done or not. Right. So this is the total work done and heat input. Right. So this is the total work done and this is a heat input. So actually, how good the conversions of the heat into work. Right. So you put the heat input and how good it converts into the work. This is the W. So this is you actually want to do achieve, and what you have to do to achieve it is the heat. Put a heat and we want to know that how it converts, how good converts into work done, and that is the efficiency of the engine tells things. Okay. So then we just put into this formula that the efficiency eta is that Q out minus Q in by Q in, that means 1 minus, sorry, yeah, so that means that Q out by Q in minus 1. Yeah. QH, and you say QH minus QL. One. Yeah, so by the conventions, this is minus. It's not a Q out minus Q in, it's Q in minus Q out. Yeah, yeah. So otherwise, yeah, so it's Q in minus Q out, and then we can say this is a Q in, this is a minus, this is plus, so it's 1 minus Q out by Q in. Let's say denoted this Q in actually QH and Q out QL. So because the same notation, TH and QH, TL and QL. The equivalence. So that is the efficiency. Okay. So now we convert in terms of the reservoir temperature. So the reservoir temperature is a I think is a good things we have to relate this eta in terms of the TH minus TL. So then we know that the process that A to B, this process is a isothermal process at a temperature TH. So I should calculate this QH. So this QH means the heat entered during this process. And let's say the volume changes from VA to VB. So it is easy to calculate RTH ln VB minus V. In the previous class, I calculated this thing that what is the delta Q. So this is a QH, is the delta Q. The amount of heat is due to this volume changes VA to VB enter through this process. And similarly B to C. So in B to C, you see that the T V to the power that is an adiabatic process. Okay. So that means that the T V to the power gamma minus 1 equals to constants for adiabatic process. So this means that pH by dl, okay, equals to Vc by Vb that whole to the power gamma minus 1, because you say that this point is a temperature, this point is temperature Th, this point is temperature Tl, this point temperature Tl, this point temperature Th, okay, and you know that this point is a volume V and this point, so we related this TV relations, okay, because this was useful. And then we need in the other two process that C2D, similarly we get QL, and so my convention is that if we hit input into the process then the positives and hit out then negatives, so minus R TL ln Vd by Vc, because we are going to compress, right? So in this case is the expansion and this is the compression. So this is the expansion and this is a compression. Okay. So that's why this gives a minus sign, because you write it in terms of ln Vd by Vc. Okay. So final volume by initial volume. So final volume is less. Okay. It's compressions due to the compression. So that's why it gives a minus sign. And the other process is D2A cyclic process. So again go back to the point A. This again TL by TH H VA by VD that whole to the power gamma minus 1. Okay. So these two equations, so let's put that in blue colors. These two equations tells that Vp by Pa Vc by Vd, right? So once you put this formula, the other two A and B, then I get that QH by QL and ln Vp by Va, ln Vd by Vc, because they are equal, so ln things are also equal. So we get that TH by T. Right? Because this minus sign actually compensated by the ln Vd by Vc is that ln Vc by Vd without minus sign. So then we can compare this. We get we end up these relations. So now if we put into the efficiency formula, so this is the eta is 1 minus TL by, sorry, 1 minus TL 1 minus Q out, yeah, 1 minus QL by QH, so TL by TH. Okay. Again, this is for the ideal gas. Okay. So we are choosing this formula, we are using this formula for the ideal gas, right? For ideal gas, and we're calculating for the Carnot cycle. This is the Carnot efficiency. This efficiency is called the Carnot efficiency. Carnot efficiency. Okay. So that means that you say that the workout, so Q is always, sorry, W is always less than equals to Q in, right, the Kelvin statement. This is a Kelvin statement. No process is possible that the heat is completely converted into the work. So that means that eta is always less than equals to 1. And its maximum for this this process. Okay. For the reversible process, it gives a maximum value, and for other real process, okay, if the irreversible contains the irreversible processes, if an engine contains an irreversible process, the efficiency is always less, and that tells the Carnot theorems. So Carnot theorems tells that Carnot's theorem tells that of all the heat engine working between two given temperature, of all the heat engine working between two given temperature, working between two given temperature, none is more efficient, none is more efficient than a Carnot engine. Okay, so this is a Carnot. Okay. So you can say that all reversible engine has the same efficiency of the Carnot efficiency. So if we take a different process, but the reversible, but not the Carnot process. Carnot process is very specific, that two isotherms and two adiabatic. But if you consider a different process, reversible process but cyclic, then the all reversible engine have the same efficiency. So I am not prove these statements, but it is easy to prove. Okay, so if you interested, then you go through this book by Blundell, Concept in Thermal Physics. So there is a proof. This the rigorous proof are there. So you just look into this if you are interested. That all reversible engine have the same efficiency, but the irreversible process, same efficiency of the Carnot. Same efficiency as the eta Carnot. So the efficiency of the Carnot engines, and if you consider any reversible process and calculate the efficiency, you say that the same. But if you consider irreversible process and the real engines, they are always less. So that means that any engine. So the final statement is that any cyclic engine is always less eta Carnot. Carnot. So if this so if this engine is reversible, then this is equals to Carnot's efficiency, and if this is not reversible, then this is less. Okay. So that's why this is less than less equal. Okay. So okay, so now our 10 minutes left, so we are going to the assignment things. So the concept in entropy we discussed in the previous class, and the Clausius statements and how to relate to the concept in entropies. Okay. So we'll do in the previous class. Okay. So now we go quickly through the assignment problems. Yeah, so the adiabatic lapse rate, I think you know that how the pressure changes from to the heights age. Okay, so this is determined by the adiabatic lapse rate. Okay, and let's do one example to calculate the efficiency quickly. Uh, yeah. So let's say an engine operates between TH. So engine operates. The engine operates between let's say TH at 800 Kelvin, 800 kelvins. Okay, and TL is 300 Kelvin. If this engine is a Carnot engine, and we calculate the efficiency, let's say this engine is a Carnot engine. Carnot, then we calculate the efficiency. Eta Carnot. So you know that the 1 minus TL by T, just put we get 60%. So just put into the formula we get it, and the other thing are there. Yeah. Okay, and again, suppose they once you know the formula that the eta Carnot, this is the total work done by total heat input, and this is again 1 minus TL by TH. So once you know this formula and you calculate the work done, okay, from the by the engines. Okay, so if this yeah, so if this Q in is provided, then you can calculate W. Right? Once you know this 1 minus TL by TH. Right? So using this formula I can calculate the most of the things. Okay. Hey, one more thing is that double and then yeah, so you calculate these things. The criteria of the reversible you know, and yeah, the concept of entropy I think. Okay, so one more thing we have to discuss that yeah. So suppose you increase the efficiency by the 2A. Okay, so the efficiency of the Carnot engine, efficiency of the Carnot engine increased. Carnot engine increased in two process in two way increased in two process, not a Carnot engine, any kind of engine. So increased in in two way. So one is that, so this 1 minus TL by TH. So that means this quantity if increase. So how to increase this Carnot engine, because TL by T increase decreases, right? This is a 1 minus. So if you decrease the TL by TH, then you can increase Carnot efficiency. But how to decrease this TL by TH? Two way. One is that if we decrease the TL to TL minus some delta T, that means either increase the temperature of the source point or decrease the temperature of the sink point. So source point means that the higher temperature, this is a source. So this is a source and this is a sink. Okay. So either increases source point temperature, that means TH, or either decreases sink point temperature, T, because we want that TL minus TH is decreases. Okay, this implies that eta increases, right? So which process is more efficient? So the question is that which process is more efficient? Yeah, can you tell me? So one process is that the TL to TL minus delta T, and another process is the TH plus delta T. So 2A. Delta T is positives. Delta T is greater than 0. So there are two ways, one way this, another. Which process is the more efficient to calculate the efficiency? So increase the efficiency. Let's say for this change, okay, the efficiency is eta 1, and for this change, the efficiency is eta 2. So then we calculate eta 1 minus eta 2. What do I get? So 1 minus TL by TH, 1 cancel. So minus TL by delta T by TH plus TL by TH plus delta. Just put, and we calculate this thing, we get that TL minus th into delta t plus delta t square divided by th into th plus delta t th tl, right? So we check that, and yeah, I think tl th th tl. Yeah, so this is right. Okay, we check this. So that means this is always greater than equals to 0. This is always greater than equals to 0 because delta t square is greater than 0, delta t greater than 0, th is greater than tl, right? So th, the higher temperature, is always greater than tl. So that means this is always greater than 0. So that means eta 1 is always greater than equals to 2. So which process is more efficient? So this process is the more efficient. Okay. Mm, 1 minute. So yeah, I think now you can solve the problems in the assignments. Yeah, any questions so far? Or any questions you are problem in the assignments? Okay. So next we will discuss the little bit about the entropy and then go to the concept. Okay, so then we will discuss some mathematical problems regarding the second law of thermodynamics. Okay. So I think you can solve the assignment problems and things. Okay, then we'll see in the next series. Thank you.